So here is question 3, and I think it's simple question, but many of you have answered in a strange way. So let me start from a general statistics. Suppose that there are two random variables A and B, and I'm going to assume that B is binary. So B takes 0 or 1, and by the law of iterated expectation, you know, expectation of A equals to expectation of conditional expectation. And now suppose that there is a function of B, say g of B, then expectation of a function of B can be written in this way. It's obvious, right? And then what you need to understand, what you do not know here is expectation of A given B is a function of B. So the randomness in A is disappeared, is integrated out. So it's simply a function of B. So expectation of A can be written as probability B equals to 1 given A B equals to 1 plus B equals to 0 given B equals to 0. And also using the same idea, you can say that the expectation of A times B can be written as expectation A B given B can be written as, so B inside the conditional expectation can come out of the conditional expectation, right? So then and remember it, you may write it as like maybe you don't need this, so it is easier to not considering that. So you can write it this way: expectation A B given B equals to 1 plus probability B equals to 0 given A B given B equals 0. So, and it is obvious that when B equals to 0, A times B is obviously 0. So this is 0, so you don't need to worry about this. And remember, when B equals to 1, A times B is always A. So it becomes this. Now, so we have two results. And part A, we are going to use this 0 equals to expectation of epsilon, which can be written as P of z equals to 1 expectation epsilon given z equals to 1 plus P z equals to 0 times expectation epsilon given z equals to 0. And so this is one thing, and another thing we have is E times Z should be 0 by the assumption, and therefore it is by the second result Pz equals to 1 times epsilon z equals to 1. So then obviously when we assume that in the question it is between 0 and 1, so this is not 0. So then for this to be 0, the only way is this equals to 0. And when this equals to 0, again, this is not 0, so this must be 0. This is how you prove this question. And the next question is similar. In part B, you would like to show that, so you need to start from this. Now it is covariance. Covariance can be written as xz minus expectation x, expectation of z. And xz can be written as pz equals to 1 times expectation x given z equals to 1. This is using the same result we used earlier, and expectation of x can be written as P1, I will simplify expectation x given z equals to 1 plus P0, expectation x given z equals to 0. And expectation of z can be written as P of 1. I think it's not that difficult. You can show that expectation of z equals to P of 1. Then you can write also, remember, this can be written as 1 minus P. I will write this as P, and then P of 0 is 1 minus P. So P, and I will simplify even more, x1 minus P times Px1 plus 1 minus P x0. And then if you calculate that, you will get P times 1 minus P x1 minus x0 is the final outcome. So P times P squared is P1 minus P, and minus P times 1 minus P. So then that's x0. So for this to be non-zero, we know that the covariance is non-zero. So then, and we know it is not zero. So then the only it cannot be zero. So then it cannot be zero either. For the final outcome to be non-zero. And see, this is pretty simple. Expectation of y given z equals to 1 is expectation of alpha plus beta x plus epsilon given z equals to 1, and it is alpha is a constant, and beta times expectation x given z equals to 1 plus expectation epsilon given z equals to 1, and we learned it equals to 0. And similarly, you can find alpha plus beta. So also, if you subtract this, and when you subtract both equations, one equation from the other, then this difference equals, and when you subtract, alpha will cancel out, and you have what you want. So simple question.